In the last video, we talked about linear transformations, and we proved a couple of functions that were linear transformations, and we looked at a few that wasn't. So now let's talk about some properties of linear transformations. So we're going to let T be a linear transformation from V onto W, and we have two vectors that are in V, and we're calling those vectors U and W. Then the following properties are going to hold. If we apply a transformation to the vector 0, it's always going to map to the 0 vector. If we need to take the transformation of negative V, that's the same thing as the negative of the transfer of V. And this makes sense because we had talked about the transformation of CV was equal to C times the transformation of V. So in this case, our C is just -1. So this guy falls right out of that piece of proving a linear transformation. And 3 kind of follows the same way. The transformation of U minus V is the transformation of U minus the transformation of V. And that's because the transformation of U plus V is true. Remember, that's the transformation of U plus the transformation of V. So if we were to look at the transformation of U minus V, we could actually view that negative, that minus as a negative. So that's equivalent to the transformation of U plus negative V, which is equivalent to the transformation of U plus the transformation of negative V. And we could view that negative as a scalar. So that's equivalent to this, which is equivalent to this. So you can see how all that's fallen out really by looking at those properties and what defines a linear transformation, where T of U plus V is equal to T of U plus T of V, and T of CV is equal to CT of V. And then the fourth one is looking at a linear combination. What if we were to take this vector V and write it as a linear combination of other vectors, V1, V2, V3, and so on? Then if we were to apply the transformation of V, then we would have to take the transformation of this side, and that's equivalent to taking the transformation excuse me, of T C1 V1 plus T C2 V2 and so on, plus T Cn Vn. And with each one of those, we know we could pull that scalar value out because of this property that holds. And so that would give us that C1 transformation of V1 plus C2 times the transformation of V2 and so on. So let's take these ideas and let's apply them to a few problems. Let's look at example 4. We're going to let T be the transformation from R3 into R3. And we know T of 1, 0, 0 is going to take us to the vector 2, -1, 4. T of 0, 1, 0 takes us to the vector 1, 5, -2. And T of 0, 0, 1 takes us to the vector 0, 3, 1. We want to find what is the transformation of the vector 2, 3, -2. So we can actually use that fourth property to help us figure that out. So let's start with this guy. It would be really easy to write that vector 2, 3, -2 in terms of these three vectors. Those are just your standard basis vectors for R3. That's vector I, J, and then K. And we can do that by looking at a linear combination there. So if we take 2 times that first vector, 1, 0, 0, that's your I vector, plus 3 times the second vector, 0, 1, 0, minus 2 times the third vector, 0, 0, 1. Then we've now written this guy in terms of a linear combination of those three vectors here. Now we know how that transformation applies, so let's take the transformation of both sides. So I'm going to take the transformation of 2, 3, negative 2. And that's going to be equivalent to the transformation of all of that stuff. So that's the same thing as taking the transformation of each piece. I'm going to go ahead and factor out those constant terms. So I take the transformation of this middle piece here, and that's going to be 3 times the transformation of 0, 1, 0. And then I take the transformation of this last piece, it's going to be negative 2 times the transformation of 0, 0, 1. And we already know what this is equivalent to. That is equivalent to the vector 2, negative 1, 4. And we know what this guy is equivalent to. That's equivalent to the vector of 1, 5, negative 2. And we know what this piece is equivalent to. That's equivalent to the vector 0, 3, 1. So then the transformation of 2, 3, negative 2 is going to be equivalent to this linear combination. So I'm going to have 4 plus 3 minus 0. Negative 2 plus 15 minus 6. And 8 minus 6 minus 2. So there's my transformation for this guy. And we got there by using that fourth property. So let's do another one then, though. Let's look at number 25. We want to find the linear transformation. So that transformation of 1, 0, 0, that's your I vector, is equal to 2, 4, negative 1. The transformation of 0, 1, 0 is equal to 1, 3, negative 2. And the transformation of 0, 0, 1 is equal to 0, negative 2, 2. We want to find the transformation of 0, 3, negative 1. So let's do that. Your first step is to figure out how can I write this vector in terms of I, j, and k. So 0, 3, negative 1 can be written as 0 times I plus 3 times j minus 1 times k. And now that we know that linear combination, we can apply a transformation here. So transformation of all of that. So that's going to be equivalent to 0 times the transformation of I plus 3 times the transformation of j minus 1 times the transformation of k. So the transformation of I is 2, 4, negative 1. The transformation of j is 1, 3, negative 2. And the transformation of k is this guy, 0, negative 2, 2. So there's our final answer. There's the transformation of 0, 3, negative 1. So it's easy peasy. We can go from one world where we were talking about the standard IJK, apply a transformation to another world, all by using that fourth property. So let's look at one that's slightly different. Let's look at 29. So if we examine this one, we're doing a transformation from R3 to R3. And if we transform the vector 1, 1, 1, that takes us to 2, 0, negative 1. If we transform the vector 0, negative 1, 2, that takes us to negative 3, 2, negative 1. And if we transform 1, 0, 1, that takes us to 1, 1, 0. And they're asking us to find a couple of images. So our approach is going to be the same. The only difference is now we're not dealing with IJK. We have other vectors here. So we've got to figure out how can we write that linear combination, because that's our first step. So we want to write the vector 2, 1, 0 as a linear combination of 1, 1, 1, 0, negative 1, 2, and 1, 0, 1. So that's going to give us a system of equations. And then if we solve that system, then that's going to tell us what our linear combination would be. So this is a 3 by 4. I got 0, negative 1, and 2. So here's what we know. We know we can write 2, 1, 0 as 0 times the first vector minus 1 times the second vector plus 2 times the third vector. So now if we take the transformation, we're going to take the transformation of both sides. And that's going to be equivalent to, and I'm going to write it this way, 0 times the transformation of 1, 1, 1 minus 1 times the transformation of 0, negative 1, and 2 plus 2 times the transformation of 1, 0, 1. And we know those pieces. We know what this guy is. It tells us the transformation of 1, 1, 1 is equal to 2, 0, negative 1. And we know the transformation of 0, negative 1, 2 is equal to negative 3, 2, negative 1. And the transformation of 1, 0, 1 is equivalent to 1, 1, 0. So if we multiply everything out, there's our vector, 5, 0, 1. So the transformation of 2, 1, 0 under this rule would give us 5, 0, 1. So that's kind of cool. It's kind of cool to see how we can use those properties to help us figure out what a transformation would look like. And we could do the same thing with number 30. So let's do that on the next page. So if we look at this one, we're still using that same set. T of 1, 1, 1 is equal to 2, 0, negative 1. T of 0, 1, negative 1, 2 is equal to negative 3, 2, negative 1. And T of 1, 0, 1 is equal to 1, 1, 0. We want to find the transformation of the vector 0 to negative 1. our first step is figure out how are we going to write 0 to negative 1 in terms of the basis vectors here. So that's where we're going to set up that combination. Or if we really wanted to, we could go back to that change of basis idea. Going from old basis to new basis and so on. But I think the linear combination is probably going to be the easiest way to tackle this one. So there's our setup. Let's do RREF. Type it in the calculator. So I got 3/2, -1/2, and -3/2. So let's talk about what we know. We now know that we can rewrite this vector 0 to -1 as 3/2 times that first vector 1, 1, 1 minus 1/2 times the second vector 0, -1, 2 minus 3/2 times the third vector 1, 0, 1. So now we could take the transformation of both sides. We're taking the transformation of all of that fun stuff. So that's going to be 3/2 times the transformation of 1, 1, 1 minus 1/2 times the transformation of 0, -1, 2 minus 3/2 times the transformation of 1, 0, 1. So all we're really doing is figuring out how can we write this transformation in terms of stuff that we know. Well, stuff that we know consists of writing that vector that we're trying to take the transformation of in terms of a linear combination, because we know how to do that. And then we also know what these transformations are because they gave it to us. So we know those pieces of the puzzle. And then it just becomes just some arithmetic that we need to complete. Transformation of 0, -1, 2 is -3 to -1. And the transformation of 1, 0, 1 is 1, 1, 1. Just kidding, 1, 1, 0. And then finish your arithmetic. And there's what I got. I'm going to clean this up. That's a -5/2 in the middle. So there's our vector 3, -5/2, -1. So it's also possible to take a linear transformation and express it in terms of a matrix. So let's look at theorem 6.2, which describes this a little bit more. We're going to let A be an n by n matrix. The function t is defined by t of v, so the transformation of v under t is equivalent to A times v. Now, if A is an n by n matrix, to make this matrix multiplication work, then V has to be an n by 1 matrix. So then our result is going to end up being an m by 1 matrix. So this is a linear transformation from Rn to Rm. V is in Rn. And then what we're going to get out is an m by 1, which makes sense that that's going to be an Rm. So let's look at an example. We're defining a transformation from R2 to R3 as follows. So the transformation of V is equal to A times V. Notice A is a 3 by 2 matrix, 3 rows, 2 columns. V1, V2, that is a 2 by 1 matrix. So we're taking this vector V that lives in 2 dimensions. And when I apply this transformation, I'm going to get something that lives in 3 dimensions. And that's because of the way that matrix multiplication is going to work out. We're going to end up with a 3 by 1 matrix here. Now, if I were to multiply this out, erase my arrow there, look what happens. We're going to have 3 times V1 plus 0 times V2. We're going to have 2V1 plus V2. And then we're going to have negative V1 minus 2V2. So there's our 3 by 1 matrix that we were talking about before. Now, we could also think about this transformation, instead of thinking about it in terms of a matrix, we could think about it this way. If we take V1, V2, and we apply this, we got that guy when we multiplied it out. So we could rewrite it this way. We're getting something that's in R3, which means it's got to have 3 pieces to it. So that first piece is that first line, 3V1 plus 0V2. That second piece is going to be 2V1 plus V2. And that third one is negative V1 minus 2V2. So we see that we can go from that matrix form. I'm going to call this guy standard form. There's not really a good way to describe that. So we could go from matrix form to standard form really just by multiplying all of this stuff out. So these two are also interchangeable. So also notice that when I started here, I could rewrite that in terms of this matrix, and then I could pull apart that matrix multiplication and go back to this guy where I have essentially a coefficient matrix times a variable matrix. So we could take anything that's written in the standard form and rewrite it in terms of matrices, or we have something that's in matrices and rewrite it in terms of standard form. So I want you to notice those connections going on here. Now in part A, they're asking us to find the transformation of V, where V is equal to the vector 2, negative 1. So transformations really can boil down to just matrix multiplication. So if we were to multiply this out, 4 minus 1 is 3. Negative 2 plus 2 is 0. So if we were to multiply these out, this is our A, that's our coefficient matrix. And then we apply the transformation and take our vector that's in R2 and multiply. We get this vector in 3 dimensions, 6, 3, 0. We would get the exact same thing if we were to take this vector 2, negative 1 and rewrite it and plug into that form. You're going to get the same answer regardless. It's just, do you want to think about it in terms of matrix multiplication, or do you want to think about it in terms of that standard form? So you've got some options now. So now let's look at a few more examples. In exercises 35 and 37, they're asking us to find the dimensions of Rn and Rm. So Rn is where we're starting, Rm is where we're going, and we've got that transformation matrix A. And we're asking, what are the dimensions of Rn and Rm? So we know that transformation for V is going to be equal to A times V. So if we look at our A here, our A is a 4 by 4. For this to be defined, then V has to be a 4 by 1. And when we multiply, we will end up with a 4 by 1 matrix. So we are starting in R4, and we are going to R4. Because this guy's where we're starting, this is where we're heading. Now let's look at 37. Same concept. I'm taking a transformation of V, and that's equal to this matrix times V. In this case, our matrix is a 3x4. So we have to think, what does V have to be so that this matrix multiplication is going to be defined? And you're right, this has to be a 4x1 matrix. So those dimensions match. And when we multiply, what are we going to get? And that's right, we're going to end up with a 3x1. So where we're starting is in R4. This is a vector that lives in R4. And then we are heading to R3.